Hello everyone, my name is Emmanuel and I'm pleased to present my project titled Short-Term Wind Power Forecasting using LSTM for microgrid operation in Bonavista, Newfoundland and Labrador. This is part of our project for our course ENGI 9857, Instrumentation and Control of Energy Systems, and our instructor for this course is Dr. Mohsin Jamil. This work explores how deep learning, specifically long short-term memory networks, LSTMs, can significantly enhance wind forecasting accuracy, which is an essential factor for remote microgrid operation. Here is an outline for today's presentation. We'll start by introduction to the problem of the project and also the objectives of the project. Then I'll walk you through the methodology that includes the data processing and model design. We'll also analyze the results of the LSTM forecast and compare these results with other standard models. We will then discuss how we converted this forecasted wind speed into wind power, because that's the end goal, to estimate how much wind power we can get from the forecasted wind speed. And then we'll wrap up with conclusions and possible future works. In microgrids, especially in rural coastal regions like Bonavista, wind power plays a vital role. However, its unpredictability poses challenges in balancing supply and demand, scheduling energy storage, and reducing reliance on diesel generators and other conventional means of generating power. Traditional statistical models like ARIMA fall short because they can't fully capture wind's chaotic nature. That's where deep learning comes into play. LSTM networks are particularly powerful because they model both short-term challenges and long-term trends in time series data, making them a strong fit for this type of problem. The study had three core objectives. First, I aimed to develop a high-performing LSTM model trained on 1 year of meteorological data from Bonavista. Second, I compared this model's performance against random forest and support vector regression, which later on I'll refer to as SVR, to assess suitability. And finally, I translated wind speed forecast into estimated wind power using turbine physics and aerodynamics. The goal is not just accurate prediction, but useful prediction for operational decisions. The dataset used in this project comes from NASA's Power database, spanning from March 2024 to May 2025, and it included the wind speed, the wind direction, surface pressure, which I termed here PS, and the temperature at 2 meters. Missing data was handled via interpolation, and I constructed a continuous time index series. I normalized all features using min-max scaling to aid model convergence. Finally, I used a 24-hour sliding window to construct the data. This means the model sees the past 24 hours to predict the next hour. Here is a snippet of the code used to normalize and find missing data. It's just a snippet of the whole code, which is lengthier than this, but just to give an overview of how the data was handled pre-processing after data collection. Let's talk about the core model used in this project, which is the LSTM model. And this is a type of recurrent neural network, otherwise called RNN, and it includes the memory cells, gates, forget gate, input gate, and output gates. These gates decide what information to keep or discard across time steps. This architecture allows LSTM networks to retain long-term trends, solving the vanishing gradient issues in other traditional recurrent neural network (RNNs) and model temporal dependencies effectively. This makes LSTM perfect for applications like wind speed forecasting, where weather dynamics evolve over time. It solves problems with non-leniency, and it handles the unpredictable nature of wind speed. Here is a snippet of the code used in creating the model. As previously mentioned, it's a part of the entire code, and it would be impossible to show the entire code here or run it on simultaneously while making this presentation. The layers are built in the code and then tested, which I'll show in the next slide. So I split the data chronologically, training on March 2024 to February 2025, and testing from March to May 2025. This simulates real forecasting where future data isn't available during training. We used the RMSE and MAE as performance metrics. They are error measurement algorithms, and the LSTM model achieved an RMSE of 0.39 meters per second wind speed and an MAE of 0.27 meters per second. Both are strong indicators of accuracy and reliability for microgrid applications. Here is a continuation of the code from the build of the LSTM model. The data is split according to the set matrix, the testing set, and then the evaluating set. So the training set and the testing set. The model is built and then trained, and the same is repeated to test against other models, standard models as the random forest and the SVR. And then we computed the RMSE errors and MAE errors, the root mean square errors, and the mean absolute error in the code. The results displayed that LSTM had the least score, and we'll delve deeper into the model comparison as the presentation goes on. And the figure here on the left shows the actual in black, although not very visible because they overlap, and the predicted wind speed from March to 2025, and also includes the RMSE range error bands. The prediction tracks the true value closely, and we can see that there's little to no lag. The LSTM doesn't over predict or under predict consistently. On the right, we see the error distribution symmetric around 0, with a little bit of deviation between -1 and 1, and this gives us the confidence in the model's generalizability and accuracy. The scatter plot of the actual wind speed against the predicted wind speed tightly clusters around the 45-degree line, which is a sign of high accuracy in prediction. Also, the kernel density model here tightly overlaps, confirming the LSTM model is not just accurate on average, but consistent across the range of speed. Here we look at how the LSTM model compares to random forest, SVR, and a basic persistent model. Persistence simply assumes the future wind equals the current one. That is the algorithm's definition. It's a useful baseline. LSTM had the lowest RMSE and MAE, outperforming persistence by about 37% and 41% respectively in terms of RMSE and MAE. But SVR showed much higher errors The random forest also did fairly well in comparison to the persistent model. This results underline the power of LSTM in capturing temporal and nonlinear patterns. In the graph here, we see how much improvement each models have over the persistent model. And in green here is the SVR. In the first time step, we have a negative improvement, which is very consistent across board. And after a 10-hour time step, we see an increase of 4% for the SVR and 11% for the random forest. The LSTM model, when this value is processed to the nearest percentage, is roughly almost the same as this, and also a slight improvement by the LSTM over the random forest, but an overall improvement against the persistent model, about 17% improvement in terms of the algorithm's ability to predict wind speed. This highlights again how strong and dependent the LSTM is in capturing temporal and non-linear patterns. So wind speed predictions are only useful if they can be turned into power estimates. Predicting the wind speed is necessary, but can only translate into useful data to us when we are able to convert this forecasted wind speed into wind power. And using a standard wind power equation right here on the bottom right, and making assumptions for the wind turbine used, for example, the Vista, the top Vista wind turbine, which has like a 40-meter rotor and a 2 megawatts rating. I computed the power outputs, and the LSTM power focus closely matched actual values, whereas the random forest and the SVR showed more deviation. This highlights the practical value of LSTM models for energy dispatch and load planning in microgrids. On the graph here, we can visibly see that the LSTM model has more visible overlap with the actual predicted wind power. The random forest also did considerably well. From the previous slide, we could see that the performance ratio of the random forest is just slightly less than the LSTM model. The SVR visibly lags the actual predicted power, the actual power by a lot in most regions. We can see over here, the region here, the SVR overpredicts the wind power, and in some other regions underpredicts the wind power. So here we look at the probability distribution of forecast errors in megawatts for each model. The LSTM has a sharp peak centered at 0, indicating tight, accurate predictions. Random forest errors are slightly more spread out, while the SVR has a much flatter, wider distribution, showing less reliable forecasting. These plots visually reinforce the numerical results from the earlier comparison slides, which showed that the LSTM and the random forest have good performance, with the LSTM having a slightly better performance than the random forest, and SVR having the worst performance amongst the algorithms. In conclusion, LSTM performed best for short-term wind forecasting in the Bonavista microgrid scenario, the data from Bonavista. Its ability to model long-term temporal relationships helped it outperform random forest, however slightly and greatly for the SVR model, and also a solid persistent model. It also translates its accurate forecast into useful wind power estimates, showing real-world applicability. These findings support the integration of LSTM into renewable energy forecasting for remote and islanded microgrids. For future research and works, several paths are promising. The model can be extended to multi-step forecasting, looking days ahead and not just hours, and having multiple layers of the LSTM models to enhance accuracy and reliability. You can also integrate solar irradiance and hybrid forecasting systems, which will improve robustness. Real-time deployment is also an option in microgrid control systems. It's also a key step that can be looked into. Also exploring ensemble models that combine LSTMs with convolutional neural networks, CNNs, or transformers. This could help push forecasting accuracy even further. I'd like to appreciate the indigenous people of Newfoundland and Labrador, our professor for this course, Dr. Mohsen Jamil, the Memorial University of Newfoundland and Labrador, and also you, my dear listener. Thank you for your time and attention. Have a great day.